Welcome back, guys. In this video, I'm going to go over scientific notation and dimensional analysis. This is part 2 of the Unit 1 remediation. So here for scientific notation, it's important that you always make sure when you're asked to put a number in scientific notation, that you use the correct system. So you want to take the decimal, wherever the decimal is located, and move it so that the main number is something between 1 and 9.999 repeating. The exponent that you put on the 10 is going to be positive if your original number is bigger than 1, and it would be negative if the original number is smaller than 1. So we got a couple to try. I have this number 940. So I want to move the decimal where it's implied to be at the end of the 0 and put it between the 9 and the 4. So now this number is something between 1 and 9.999. So I got 9.40, and it is important to include zeros if they're significant. But here's the thing, that 0 is not a significant 0 in this number because it's trailing and there's no decimal. So when you convert to scientific notation, you actually would not include that as part of your scientific notation. But you can't just say that the answer is 9.40 because 9.4 is not the same as 940. So we say this is multiplied by 10 to however many places we had to move the decimal. So the original number was 940. We moved that decimal over 2 places, so we raise this to the second power. This number is greater than 1, so my exponent here should be to the positive second power. So let me write that without all the scribbles. So we would say this is 9.4 times 10 to the second power. And notice that my number in scientific notation has the same number of sig figs as my number not in scientific notation. There are 2 significant digits and 2 here. What about this one? This number is much smaller than 1, but I'm still going to move my decimal and stick it in a place to make the main number something between 1 and 9.999. So I put my decimal between that 7 and 3, but the 0 at the end is a significant 0. If it wasn't a significant digit, they wouldn't have put it there. So we have to include it in our scientific notation. So I put 7.30, and then I got to do times 10 to some power. And it's the number of places that that decimal had to move to get into that location, which looks like 4 places. We move that decimal over. But this number originally was less than 1, so this should be a negative exponent. So we got 7.30 times 10 to the negative 4th power. And lastly, we're going to go through some dimensional analysis practice. This seems like where most people struggled. All dimensional analysis is, it's a fancy way to say that we're going to convert our units from one unit to something else. And some key factors to remember. We talked about 1 mole of anything. The word mole is just a way that we can group a bunch of stuff into a nice little package. And so a mole of anything is going to have 6.02 times 10 to the 23rd particles in it. And we discussed how the word particles can mean it's the same as saying atoms or molecules or formula units or ions. So all those terms mean the same thing. And then 1 mole of a substance has a mass specific to the molar mass, which we calculated out and practiced doing that in the previous video. So when you're approaching one of these questions, say I've got 5.3 moles of Na, which is sodium, and I want to know how many atoms that is. Nowhere in this problem is mass or grams mentioned, which means you do not need the molar mass. It does not matter that this substance is sodium because 1 mole of anything has 6.023 times 10 to the 23rd atoms to it. So what this is asking is how many atoms are in 5.3 moles. So we write down our original number because we want to convert. And we know that moles has to go away. So I'm going to put moles as a unit on the bottom. And I have already said that 1 mole of anything contains 6.02 times 10 to the 23rd power atoms. So now I just have to multiply 5.3 times 6.02 E23 over the number 1. And when I do that, making sure to use my E button, times 6.02 times 10 to the 23rd, I get 3.1906 times 10 to the 24th power. And this is atoms. But it is important that you double check your sig figs. Your sig figs should always be based on the number of sig figs in your original number, which here is 2. So I need to round this answer to 2 sig figs. So rounding this answer to 2 sig figs, I get 3.1, but the 9 rounds it up. So I would say this is 3.2 times 10 to the 24th atoms. So let's go backwards. Let's go the other direction. Here now I have molecules and I want to know what that's equal to in moles. So 4.3 times 10 to the 24 molecules of KCl. It doesn't matter that it's KCl because molecules in moles is always going to use the same conversion factor. I've got molecules on the top this time, which means every 1 mole contains 6.02 times 10 to the 23rd molecules on the bottom. So now this is division. This number divided by that number using your E button in your calculator. 24 divided by 6.02 E23 will give you 7.14286 and a few more decimal places. But we want to pay attention to our significant digits. Our original number had 2 sig figs in it, so our answer needs to have 2 sig figs. So this is significant, this is significant. Check your next digit over. It does not. It's not large enough to cause it to round, so we would report our answer as 7.1 moles. So now what about if you have mass involved? Here I'm including, I want grams. Since I see grams, I have to know the molar mass of that chlorine, that Cl2. There's 2 of them. So I check the periodic table. I find that the average atomic mass of chlorine is 35.453 or thereabout. And so when I multiply, I get that the molar mass is 70.906 grams per mole. So if I take 3.2 moles of chlorine, and I know that every 1 mole has this mass of 70.906, then 1 mole will go on the bottom because I need this to cancel, and 70.906 grams will go on the top. So multiply that out times 3.2 gives us 226.8992 grams. Looking to our sig figs, again the original number has 2 sig figs, so this answer needs to round to 2 sig figs. So the first digit, the second digit, check the next one over to see if it rounds. It does. So we say this is 2, 3, and then we can't just call it 23, so we put in a placeholder 0, and as long as you don't put a decimal there, that 0 is not significant. So the number 230 does have 2 sig figs, and it's close to this number 226. So we have that mass of Cl2 produced. What if you're going the other direction, from grams to moles? Well, since grams is present in the problem, you have to know the molar mass of that H2O. So we have 2 hydrogens, each at 1.008 grams. We got 1 oxygen at 15.999 grams. So when you multiply and add that stuff together, you get that water has a molar mass of 18.015 grams per mole. So I take my original number, which is 12.3 grams of H2O, start my train track. I need grams to cancel, so I gotta put the grams on the bottom. So every 1 mole weighs 18.015 grams. That's for every 1 mole of water. So now this is division. This number is on top, that one is on bottom. The 1 doesn't really affect anything. So I take 12.3 divided by 18.015, and I come up with 0.68276 and a few more decimal places after that. This would be moles, but again, we check our sig figs. There are 3 in the original problem, which means our answer can only go to 3. So this is 1, 2, 3 sig figs. Check the next number over. That 7 does cause rounding up, so we would report our answer as 0.683 moles of H2O. And remember, a leading 0 never counts, so it's okay for me to put that 0 there. It's not significant, so it's not affecting the problem. Okay, last one. So what if we have molecules? So I know I've got to use that 6.02 times 10 to the 23rd number, and I have grams. So I know I have to know the molar mass. This is a 2-step problem. So let's find the molar mass of NaCl. There's 1 Na at 22.990. That number comes from the periodic table. I add that to 1 Cl at 35.453, and I come up with 58.443 grams per mole, for the NaCl. So every 1 mole of NaCl is going to have a mass of 58.443 grams. Every 1 mole of NaCl is going to contain 6.02 times 10 to the 23rd molecules. So if I have 2.9 times 10 to the 25th molecules of NaCl, the question is, what does that weigh? What is the mass of that? So what I have to do is I have to figure out how many moles I have of that first. So I'm starting with molecules. I need molecules to cancel. So I will put the unit molecules on the bottom. And the number that goes with molecules is 6.02 times 10 to the 23rd molecules on the bottom. And that's equal to 1 mole. So this will tell me how many moles of NaCl I have. Now I could solve this out and then do a whole nother step, or I can add another section to my train tracks. These molecules have canceled. Now I need to get rid of moles because I want to know what this is in grams. So I got to put moles on the bottom now. And I know that the mass of 1 mole of NaCl is 58.443 grams. So these moles cancel, and if I do all the math with the numbers, the only unit that's left is grams of NaCl, which is good because that's what I want. That's what I'm solving for. So remember, this line right here is like essentially setting up a fraction. You have the top numbers over the bottom numbers. These vertical lines, these are multiplication. So I'm going to multiply some numbers. I'm going to take 2.9. I'm going to put my screen in here so you can see it, hopefully. There's a bit of a glare. 2.9 times 10 to the 25th. And then we said that's times 1, and then times 58.443. Times 58.443. Go ahead and hit enter. So that's the product of the top, or the numerator. Well, that's all divided by 6.02 times 10 to the 23rd. So I'll hit divide, 6.02 E23, and I come up with this answer. So this comes out to be 2815.36045. And this was in grams of NaCl. But again, we check our sig figs. Our original number only has 2 sig figs in it, which means this number has to have 2 sig figs. So start reading from the left to the right. The first digit is going to be significant. The second one has to be significant. I look at my third one over to see if it causes a rounding. The number 1 does not cause the number 8 to round up. So I replace the rest of this with placeholder zeros. So the number 2, 8, 0, 0, and that's it. These zeros are not significant because they're trailing and there's no decimal. So the number 2800 does have 2 sig figs, which matches my original problem. And then, of course, we always include units and labels to be completely correct.